In the last video, we talked about infinite limits. So as our function approached some x value, our graph was growing off to infinity or off to negative infinity. But in this video, we're going to be looking at what's happening to our graph as x goes off to infinity. What's happening to the y value. So if we take a look at this curve here, we can see that, and we can see it also represented in the table. As my x values are going off to infinity, right, as x is getting larger and larger and larger, my y values are kind of leveling off a little bit. So my y values come up here and they kind of level off, and they're approaching this y value, getting closer and closer to this y value here of 3. And we can see the same thing happening in the negative direction. As x is going to negative infinity, my y values are getting closer and closer to negative infinity here, right? We can see that there as well. So as x goes off to, getting closer and closer to 3 as x is getting closer to negative infinity. So as x is going off to negative infinity, this is also approaching 3. This idea of it approaching this horizontal line is the idea of a horizontal asymptote. So it's getting closer to this y value, and as the x values are getting larger and larger and larger. So my limit as x approaches infinity of f of x is 3, and it's the same on the other side as I approach negative infinity. Now that's not always going to be true. There are some functions that have a different horizontal asymptote on the right-hand side than the left-hand side. So you do have to check the limits on both ends. And this idea of limits at infinity essentially is us considering what we call end behavior of our function. So in this next example, we're going to be taking a look at finding some limits using tables and graphs. So I'm going to pull out my graphing calculator. So let's take a look at the graphing calculator here. And I want to plug in the graph of sine of x over x. So we're going to go into y equals, type in sine of x, close our parentheses, divided by x. Let's clear out the rest of this up here. So we just want to have sine of x over x. Now again, remember in our table, we want it to be asking us for our independent variable. So you can go second window into table set and have it ask. And let's go ahead and look at our table. Actually, first let's just look at the graph. So this is what the graph looks like. It kind of has this little bump here in the middle, and then it kind of oscillates about the x-axis. But what does that look like from a table point of view? So as we're getting going off to positive and negative infinity, that means our x values are going to be getting larger and larger and larger. So if I plug in something like 1, I get this, 100 or 10. What happens at 10? 100, 1,000. Getting big. So basically, you can see that these numbers are getting this e to the negative 7 essentially means it's scientific notation. So we would be moving this decimal place 7 units to the left. So our numbers are getting smaller and smaller and smaller. Now you can see that they're kind of oscillating between positive and negative, and that's because the graph goes back and forth between this here. But basically what's happening is, because the numerator is kind of bound between 1 and negative 1, it's going to not really change a whole lot, and my denominator is getting larger and larger and larger. So if I have something between 1 and negative 1 being divided by a huge number, then that means that this is going to be going off to 0. Right? It's getting closer and closer and closer to 0. It's getting smaller and smaller and smaller as my denominator gets increasingly large. Okay, so let's take a look at this example. We want to use graphs and tables to find this limit. The limit as x approaches infinity of x divided by the square root of x squared plus 1. So again, we can go back into our graphing calculator, go into y equals, and we'll clear out the y1, and we'll type in this function. So x divided by, and then we have the square root, so you can put parentheses, square root of x squared plus 1. And we can tab out of that and close our parentheses. So if we look at the graph here, we can see that as x goes off to positive infinity, it looks like it's kind of leveling out here. And as x is going off to negative infinity, it kind of levels out here again as well. So let's go ahead and get into the table. And actually for this one, I'm not going to make it so that I have to manually type in numbers. Instead, I'm going to adjust my table set so that it goes at increasingly larger values so that the space between them is large. So I'm going to say auto, and I'm going to have the table start at 0 but go by hundreds. So every increment is going to be 100 units. So what happens if I look at the table there? So as my values are getting larger and larger and larger, it's essentially telling us that it's 1. But if you go over to the y values here, you can see that it's not actually 1, right? It's numbers that are getting closer and closer and closer to 1, but it's not actually 1. And so our limit, as we're going off to infinity, right, our number is approaching this horizontal asymptote of 1. What if we were going in the negative direction? So again, let's bring out our calculator again. Right, we saw in the graph that as I go in the negative direction, it's also kind of looking like it's leveling off here. So let's go in the negative direction and take a look at our table again. Let's start again at 0, going by hundreds, and looking at our graph, but this time going in the other direction. So we can see that it says it's going off to -1, but again, it's not actually -1, it's just that's the number that it's approaching. Whoops. So as we go here, the numbers are getting more and more and more negative, right? Closer and closer and closer to -1. So this is getting closer to -1. So that means that this function has a horizontal asymptote at +1 and then at -1 as you go to the different sides of infinity. All right. Which kind of brings us to the definition of a horizontal asymptote. So we say the line y equals L is a horizontal asymptote of our graph if my limit as I approach either negative infinity or positive infinity is L. Now, L is a finite value here, just like it was in our limits. So if our function approaches some finite value as x goes off to positive or negative infinity, we say that that finite value y equals L represents a horizontal asymptote. Some other rules regarding limits at infinity. So if r is a positive rational number, so it's something that can be written as a fraction, and c represents any real number, then this is true. So the limit as x approaches infinity of some real number divided by x to some rational number is 0. So as my denominator essentially becomes larger and larger and larger and larger, if I have some constant being divided by some really, really big number, then it's going to be 0. And the same is going to be true going in the other direction. If x is approaching negative infinity, even if it's a negative number, you take a really, really, really big negative number and divide something constant by it, it is essentially 0. So that limit would be 0. So this says the second limit is only valid if x to the r is defined when x is negative, right? So this has to be defined in order for that to exist. And another limit that we can look at, so if you think about the function, the exponential function, the graph of the exponential function looks something like this, right? And we know that as x is approaching negative infinity, as we go in this direction, we have that horizontal asymptote at the x-axis, and that's essentially what this is saying. The limit as x goes to negative infinity of e to the x is 0. And then the limit as x approaches positive infinity of e to the negative x is 0. This negative x basically reflects the graph of the exponential function about the y-axis, and so it would look like this. And so that would also go to 0. All right, so let's use some of these properties to help us evaluate some limits. So we want to find the limit as x goes to negative infinity of 7 minus 1 over x squared. So I can break that kind of up into two different limits. It's going to be the limit as x goes to negative infinity of this constant minus the limit as x goes to negative infinity of 1 over x squared. So the limit of a constant is always just the value of our constant. And then this is one of our limit rules. It said if I have some constant divided by this value going off to positive or negative infinity, then that would be 0. So because this number is getting bigger and bigger and bigger if I plug in negative infinity. So 1 over a really big number is going to be 0. So 7 minus 0, which means this limit is 7. If I plug in infinity here, this gives me e to the infinity minus 6. E to the infinity is just infinity, right? It's getting larger and larger and larger, minus 6. So if I subtract 6 from infinity, that doesn't really have any impact on the limit. So that would be infinity. In this example, we want to look at these are polynomial functions, and we want to look at the limits as we approach the right side, right, as x gets larger and larger to positive infinity, and then as x gets more and more negative to negative infinity. Now, one thing that's kind of interesting about rational functions is we only really care about the highest degree term. These numbers are basically insignificant as x is approaching really, really large numbers. If I'm plugging in a positive infinity here, these values are really having very little impact compared to this. And so my whole function is going to behave based entirely on this leading term. So you've probably seen that idea of end behavior in pre-calculus where you only had to look at the leading term, and that's kind of why this happens. Okay, so what is my limit as x approaches positive infinity of f of x? So in doing that, it's basically going to be the same as the limit as x approaches positive infinity of 4x to the third, because these other, like I said, these other terms become pretty much insignificant. And if I cube infinity, it's just going to be a bigger number. And then I multiply by 4, again, it's just going to be a bigger number. So that limit would be positive infinity. But if I look at this limit as x approaches negative infinity of f of x, it's essentially, like I said, the limit as x is approaching negative infinity of 4x, x to the third. When I plug a negative number in and I cube it, a negative number cubed is a really, really big negative number. And then a big negative number times a positive number is going to be something negative. So this would be negative infinity. And this kind of matches what we know about cubic functions, right? If the leading coefficient is positive, we know that as x goes off to negative infinity, the y values are going off to negative infinity. And as x goes off to positive infinity, the y values are going off to positive infinity. What about in something like this, where we have a negative 5x to the fourth? Again, when evaluating the limits, I don't really care about these other terms because they're insignificant as far as in the end behavior. So the limit as x approaches positive infinity of f of x is going to be the same as the limit as x approaches positive infinity of negative 5x to the fourth. When I plug positive infinity here, x to the fourth, that's going to be positive infinity. But now we're multiplying by a negative number, so this is going to be negative infinity. So that limit would be negative infinity. And then the limit as x is approaching negative infinity of f of x is essentially just the same as the limit as x approaches negative infinity of our first term, of our highest degree term, right? So plugging in a negative infinity to an even power is going to make it positive. And then so we have a really big positive number times a negative number, which is again going to be negative. So we'd get negative infinity here. And that kind of makes sense too, right? We know that a even function is going to either start high, end high, or start low, end low. And this leading term is going to dictate that. So because it's negative, it starts low and ends low as x goes from negative to negative and positive infinity. If you remember your rules about rational functions, you might also consider or remember the rules about horizontal asymptotes. So we had a rule about horizontal asymptotes where if the numerator's degree was greater than the denominator's degree, then the limit of our function, or then the horizontal asymptote, was 0. So this is, let's take a look at why that is. So we have an assumption, or we have an idea that this is going to be going off to 0 as we go off to positive and negative infinity. But why does that happen? So I am assuming that the limit as x goes to infinity of f of x, or I'm presuming, not assuming, is going to be 0 for both of these. The limit as x goes to negative infinity of f of x is going to be 0. Now, why is that? So the way that we can verify this analytically is by taking all of these terms and dividing by the highest degree in our denominator. So if I divide by my highest degree in my denominator, I'm going to get, divide everything by x squared. I'm going to get that f of x is going to be equivalent to negative x over x squared plus 4 over x squared. And then we have 5x squared over x squared, and then plus 2 over x squared. I just want to show this the first time, and then we'll just be able to reduce these things kind of on our own. So this is going to cancel, and we're going to have 1 over x there. This is going to stay like this. These x squareds will cancel, and then we have something like that. So when we're looking at this, this is essentially 1 over x plus 4 over x squared. Actually, it should be negative, though. And then divided by 5 plus 2 over x squared. And if I wanted to take the limit of this, right, if I wanted to take the limit of this, the limit as x goes to positive infinity, what happens? So if I plug infinity in here, this piece becomes 0. Remember, a constant divided by something going to infinity is 0. If I plug it in here, again, 4 divided by something going to infinity, that is also 0. This is just a constant, so its limit is itself. And then 2 divided by something going off to infinity is 0. So I end up with 0 over 5, which is 0. So that confirms this one. What if I did it off to negative infinity? So I'm going to quickly copy this here. Actually, I'm going to copy this whole thing. So if I did this off to negative infinity, what do I get here? So it's going off to negative infinity now. So negative infinity, this is going to still go to 0. This is still going to go to 0. This is still going to be 5, and that's still going to go to 0. So again, I get 0. So we've confirmed that one as well. Okay. Do you remember the rule when it said if the highest degree term, if the numerator's degree is higher than the denominator's degree? So generally we would say that this has no horizontal asymptote. And what does that actually mean as far as our function is concerned? What is the end behavior going to look like? So as I go off to infinity, what's happening? Well, basically, in this last problem here, right, we could have just looked at these first two terms and ignored these because they're pretty much insignificant and reduced, right? So if we did that, we'd end up with negative 1 over 5x. If I plug in infinity in this is going to give me 0. If I plug in negative infinity in that, it's going to give me 0. This whole process here is the more analytical approach, and that's the way that you should be checking your limits. But this gives us the general behavior. It's kind of a little shortcut. So we can use that same idea, the shortcut here, to check our behavior here. So we basically only have to look at those, the highest degree terms. And if I wanted to evaluate the limit of f of x, the limit as x goes to infinity of f of x, it's basically going to be the same as the limit of just the quotient of those highest degree terms, 2x to the 6th over 5x to the 4th. So let's go ahead and reduce this. I'm going to get the limit as x approaches infinity of 2x squared over 5. And if I plug an infinity into this, this is going off to infinity. So it's growing off into infinity forever. If I evaluate the limit as x goes to negative infinity for this, again, I can look at just the highest degree terms in the numerator and denominator. It's the same as the limit as x is going to negative infinity of 2x to the 6th over 5x to the 4th, which, when we reduce this, is, again, 2x squared over 5. Plugging in a negative infinity, this is still positive times a positive, divided by a positive, that's all positive infinity. So that would be positive infinity there. So as we go off to positive and negative infinity, since the numerator's degree is larger than the denominator's degree, it's going to go off to infinity. It could potentially go to negative infinity, but it's basically you just look at the signs. If it's a positive divided by a positive, then it goes to positive infinity. If it was a negative divided by a negative, again, it would go to positive infinity. But if the signs are different, then it would go to negative infinity when the numerator's degree is larger than the denominators. Do you remember the rule when they were equal? What happens when they're equal? So looking at just those, because again, these are insignificant as far as the limit's concerned, as we're going off to infinity and negative infinity. So the limit here, as x is going off to infinity of f, is going to be the same as the limit as x goes to infinity of the quotient of just our highest degree terms. If we reduce this, we end up seeing that it's looking at the limit as x goes to infinity of 3/5. And the limit of a constant we know is just a constant. So that rule basically says if you have the same degree in top and bottom, you just take the quotient of the highest degree terms. And we can also show that in the negative direction. So the work is basically the same thing, but you do need to show both directions because it is not always going to be the same. It will not always, it will not always be the same. So you do have to check both directions in all of these problems when it's asking you to find horizontal asymptotes. So 3/5 would be a horizontal asymptote. In this example, there are no horizontal asymptotes. In this example, the horizontal asymptote would be at 0, at y equals 0. Now these ones get interesting. So now we have a square root of something squared here. So we want to find the limit as x approaches positive and negative infinity of this here. Now if you think about the square root of something squared, generally we say that that is just the equivalent to x, right? So if I multiply something inside of it like this, then that's essentially like saying the square root of 3 times x. Now you have to be careful in these situations because this whole idea comes from the fact that, like, okay, what if we had the square root of, or what if we had something like x squared equals 10, right? X squared equals 10. If I wanted to get x from this, I could take the square root of both sides. But in doing so, I would have to take the positive and negative square root. So we have to ask ourselves, when do I use the positive value and when do I use the negative value? So the same issue arises in this situation. And when x is going off to positive infinity, the square root of x squared is just going to be equal to x when x goes to positive infinity. When x goes to negative infinity, the square root of x squared is going to be the negative x. So it's the opposite version. So in this situation, we don't have to worry about the negative because we have a positive infinity here. So really this piece right here is kind of like saying rad 3 times x as far as its degree. And so it would be its highest degree term in the numerator. And then this would be the highest degree term in the denominator. Now, if you wanted to look at this in the more analytic approach, we'd essentially divide everything by x, by the highest degree term in the denominator. And what would that look like? So in the denominator, it would end up being 5 divided by x. And then dividing this by x is just going to give me negative 2. In the numerator, it's going to be 3x squared plus 6. Now, when I divide by x, since I'm inside the square root, I actually have to divide by like a square root of x squared. So inside the denominator, it's going to be an x squared like this. We're taking the limit here. Let me move this out. We're taking the limit of this as x goes to infinity. So this is going to actually end up being the square root of 3 plus 6 over x squared all over 5 over x minus 2, and evaluate this limit. Sorry guys, getting lazy with my limits here. So now when I plug in my infinity, what happens? Well, this stays 3. 6 divided by infinity is going to be 0. And then 5 divided by infinity is going to be 0. And then that stays as negative 2. So this whole thing ends up being the square root of 3 over negative 2. So we really could have just looked at what we started with here. Right? We could have just looked at what we started with here and considered the square root of 3x squared over negative 2x. We just had to remember that the square root of 3x squared is equal to the positive rad 3 times x when x is going to infinity. And it would be negative rad 3 times x as x goes to negative infinity, which we'll see in the next example. So those would have canceled and we would have gotten rad 3 over 2. Right, so if we consider that same idea, but now we're going off to negative infinity, I could say, okay, this would be the same as the limit as x goes to negative infinity of rad 3 x squared over negative 2. But since x is going to negative infinity, this is the same as the limit as x goes to negative infinity of negative rad 3, or sorry, let me just say it like this. Rad 3 times negative x all over negative 2x. Right, because as x goes to negative infinity, that's when we have to use the negative version of this. And then we could cancel this with this. And we have a negative 1 here times rad 3, so that these can become positive. So this limit would end up being positive rad 3 over 2. So this would have a horizontal asymptote at positive rad 3 over 2 as we go to negative infinity. And then this one would have a horizontal asymptote at negative rad 3 over 2 as we go to positive infinity. All right, so let's look at this last example. So f of x equals 1 over 1 plus e to the x. If I just go in and try and use direct substitution, what happens? I'm going to get, so let's, so it's saying show that this has 2 horizontal asymptotes. So that means I have to look at the limit as x approaches infinity and the limit as x approaches negative infinity of f of x. Okay. So if I plug in infinity here, I'm going to get 1 over 1 plus e to the negative infinity. But a negative exponent we can think of, right, e to the negative infinity is the same as 1 over e to the positive infinity. And this number is just going off to infinity, so this whole thing is 0. So this is 1 over 1 plus 0, which is just going to be 1. Now if I plug in a negative infinity, it's 1 over 1 plus e to the opposite of negative infinity, which is going to be positive infinity. E to the infinity is infinity. So that's going to be 1 plus infinity, which is just infinity. So 1 over infinity is 0. So we have a horizontal asymptote of 1 as we go off to infinity, and then a horizontal asymptote of 0 as we go off to negative infinity.